For today's lesson, we're going to derive the equation of an ellipse. Recall that the equation of a circle centered at the origin is x squared plus y squared equals r squared. So, in this situation, we have the origin 0, 0, and this would be the radius r. A circle is a special case of an ellipse because if you take the equation of a circle and divide everything by the radius squared, you wind up with a standard equation of an ellipse. This is a special case because the radii have the same length. Because in the circle, it doesn't matter where you draw the radius. It's going to be the same distance. But in general, in an ellipse, that's not always the case. It's going to be more of a stretched out circle. So in general, in the ellipse, radii differ in length. In general, if it's centered around the origin here, we have x squared over a squared plus y squared over b squared equals 1. And I picked two different variables represents the radii because they could differ in length. For example, if the radius a is greater than the radius b, we're going to get a horizontal ellipse. So the distance from here to here would be a, and the vertical distance would be b. And anytime a, this radii, this number here under the x squared is greater than the radii of under y squared, it's always going to be a horizontal ellipse. Likewise, you get a vertical ellipse when b is greater than a, for example. If this number is greater than a, then you get a vertical ellipse. So let's say that's the origin. This is the distance b from here to here. And this distance here will be a. Now, anytime you see the longer side of the ellipse, that's called the major axis. In this case, it will be b. And the minor axis is the shorter distance. So, in this case, the minor axis is a. Alright, the foci of an ellipse is a set of points on the major axis that are symmetrical to the center. In this case, the center is still the origin. And the foci points, let's say, is right here. I'm going to call this F1 and F2. And since it's symmetrical, this y-axis is going to split it into two even parts. So, for example, the distance here is going to be the same as the distance here. So let's say this has a distance at a. This is going to have a distance at a. And let's say the vertical height is b. So what you have here is a right triangle. You have a height of b, and hypotenuse of A, and let's say let's call this F. If you find out what one foci point is, you just put the negative sign to the other because it's symmetrical. So in general, if I want to figure out what the foci point is, I'm going to use the Pythagorean Theorem. So that's the square of the hypotenuse is equal to the sum of the square of the legs. And what you're going to do is solve for f. So I have f squared equals b squared minus a squared. So what you wind up having is f equals the square root of b squared minus a squared. And you can use this to figure out the foci point, the focus points. For example, it says find the focus point of the given ellipse. And we're assuming this is centered around the origin because you just have x squared and plus y squared at the top. So you want to think of it like this. So you want to take the square root of 25 to figure out what a is. So we know the square root of 25 is 5. You can think of that as 5 squared or 3 squared here. The square root of 9 is 3. So what we're saying is this distance is negative 5 here. This is 5. It goes up 3 and down negative 3. But you want to figure out the focus points. You're going to use that formula I showed you earlier. So you're going to say f is equal to the square root. In this case, you got to put 25 minus 9 because you can't have a negative in the square root. This is going to be the square root of 16. So the focus point is going to be 4. So negative 4 and 4. In general, though, an ellipse is not always centered about the origin. So in that case, we use h and k, depending on how if it moves to the left or to the right. So this is the general equation of an ellipse. This concludes our lesson for today.